Okay, so this is going to be section 14.7 from chapter 14 on game theory. In this section, we're going to be covering the Shapley value. So basically building off of 14.6 when we covered the core of an n-person game, now we're going to be talking about the Shapley value, which in general is just going to be a more equitable solution than what the core offers. So whereas the core gives us kind of a collection of feasible solutions, this Shapley value is going to be a single reward vector. And let me change my color. Single reward vector here. And it's going to satisfy a couple of these axioms here that ensure that this is a unique reward vector. So our first axiom is going to be relabeling of players interchanges the player's rewards. So suppose that you have a reward vector of 10, 15, and 20. If you switch player 1 and player 3, the roles or the values inside of that reward vector will switch to 20, 15, 10. So basically just rewards in the solutions are going to be dependent on player assignment. For axiom number 2, we just have basically group rationality. So all of this really is saying here is the sum of all the players' rewards is equal to the total reward for all players. So I'm going to write that on the side here. Sum of all players' rewards is going to be equal to the total reward for all players, which really just is saying that all of the prize essentially is going to be used and divvied up amongst the players. Axiom 3 is basically just talking about if we remove a player I from our coalition S here, if him leaving the coalition does not change the total reward, then he deserves 0 reward. Because what that's saying is this player I is not essential and contributing nothing, so therefore they don't deserve any reward. And then finally, axiom 4 is going to be let x be the Shapley value vector for game V and let y be the Shapley value vector for game U. Then the Shapley value for game V plus U is going to be the vector x plus y. So all this is saying is adding together two games, there's the Shapley value, or like the characteristic function basically, of the sum of both the Shapley values. So really it's just, it kind of makes sense if you think about it. It might be a little bit weird because adding games seems like adding apples to oranges, but really it works out. There's a proof behind it in the textbook if you want to look into it, but I didn't feel it was necessary here. And then finally, we do have this general equation to find Shapley value. However, I do find that rather than using this equation, there's a much easier way to evaluate the Shapley value numbers in the reward vector if you just use order of arrival principles here, which I'm going to show you in this example. So for our first example, Joe Willie has invented a new drug. Joe cannot manufacture the drug himself, but he can sell the drug's formula to Company 2 or Company 3. The lucky company will split a $1 million profit with Joe Willie. Now find the Shapley value for this game. So we're going to start off here. Again, I mentioned how we're going to be talking about order of arrival. So we do have a total of 3 players here in this game. So if we're looking at the different possibilities for ways these people can arrive, that's just going to be 3 factorial, or in this case, there's 6 ways. 3 times 2 times 1. So I'm going to start off here by just kind of listing out the total number of ways that we can have people show up to this coalition here. So it starts off, we could go player 1, Joe, then player 2, then player 3. We could go player 1, player 3, player 2, 2, 1, 3, and 2, 3, 1. Or finally, we could go 3, 1, 2, or 3, 2, 1. So this is again just basically is saying, for this first example, we have player 1 showing up, and then to follow we have player 2 arriving, and we're going to kind of just show what happens when player 2 arrives, and then what happens when player 3 arrives respectively here. Get rid of those. So now on these next parts here, I'm going to write the amount added by player arrival. So again, I'll just kind of show you what this all means here. So we have player 1, player 2, and player 3. So in this first scenario here, if we just have, so player 1 is going to arrive first here for us. And when it's just player 1, we said Joe can't manufacture the drug by himself. So at this point, the prize is $0. Player 1 has added nothing. Now when player 2 arrives, we know that company 2 and Joe together can make that $1 million profit. So player 2 has contributed $1 million to this coalition. And now when player 3 arrives last, there's no additional reward as this guy shows up. So just a 0 here for him as well. On to the next one. Again, player 1 by himself has nothing. Player 3 shows up now. So he's contributing $1 million. And then when player 2 finally comes, there's nothing that he's adding. For this next one, player 2 starts off. So again, the company can't do anything without the formula. Now Joe is showing up, which is bringing that $1 million value. And then player 3 comes, which adds nothing. Then in this one, we have player 2 arriving, which doesn't have the formula. Player 3 follows. They still don't have the formula here. And then finally, Joe arrives. So there's that $1 million added amount to the reward. And then in this case, player 3, 0. Player 1 arrives, so there's that $1 million. And then player 2, 0. And then lastly, player 3, player 2, and player 1 has the formula. So now they have that reward. So now that we've kind of broken down all of these different orders of arrival that we could have and how much the reward is supposed to be, it's important to note that all of these orders of arrival, all of them have equal probability because we don't know which of these people are going to be in the coalition. We should treat them all equally. So now what we're doing is, in order to find the amount that player 1 should make, we're going to sum up all of these amounts that they're adding and then divide it by the total number of arrivals, which is 6 in this case. So here for player 1, we've got 4 million divided by 6. Then for player 2, we've got just 1 million divided by 6. And similarly for player 3, we've got again 1 million divided by 6, just from summing up all those numbers in that column and dividing it by the total number of rows, which is 6. So then finally we can make our Shapley reward vector here, which is just going to be 4 million over 6, 1 million over 6, and 1 million over 6. So ultimately what this reward vector is telling us is this is the most suitable rewards here for everyone to have a fair share given what they are contributing to this coalition. And if you do sum up all three of these x1, x2, x3 values here, it does give us that $1 million amount that we're working with. So it makes perfect sense, basically. So moving forward here, we do have the problem. Suppose there are 3 types of planes: Piper Cubs, DC-10s, and 707s, using an airport. A Piper Club requires a 100-yard runway, a DC-10 requires a 150-yard runway, and a 707 requires a 400-yard runway. Suppose the cost in dollars of maintaining a runway for 1 year is equal to the length of the runway. Because 707s land at the airport will have a 400-yard runway. For simplicity, suppose that each year only 1 plane of each type lands at the airport. How much of the $400 annual maintenance cost should be charged to each plane? So again, we're going to start off with that same concept here. I'm going to actually first assign player roles to each of these types of planes. So we're going to say Piper Cubs are going to be P1, DC 10s are going to be P2, and then 707s are going to be P3. And now, again, we're going to have 3 factorial or 6 orders of arrival here. And I'm going to, again, just make that same table basically we had in that first example. Order of arrival. So we can go 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, or 3, 2, 1. Those are our 6 ways that we can have players arrive in the coalition. And then again, we've got amount added by player arrival for player 1, player 2, and player 3. So in the first case here, we have player 1 arriving first, which is the Piper Cub, and they require a 100-yard runway. So what that's saying is, since we said the cost of maintaining the runway is equal to the length of the runway, at this point the Piper Cub owes $100, because that's all they need for just that type of plane. Now the next one that arrives is player 2, which is DC 10s, and DC 10s are going to require 150 yards. So now we just take the difference between that 150 they need and the 100 that's already there, and they should be paying 50. And now finally, when player 3 arrives, which is the 707s, 707s require 400 yards. So now we take 400 minus the 150, and we have 250 that player 3 should be contributing, or the 707s. So the next one here we have, again, starting with player 1, $100 going towards the runway. Then for player 3, we jump ahead and we need $400 now, so they should put forward 300. And at this point, when player 2 arrives, we already have the 400-yard runway, so they are paying nothing. Next, we have player 2 going first here, so they start off with their 150-yard runway. Player 1 comes along, they only need 100, so they're good. And then player 3 arrives, and they need to pay that remaining 250 to get up to that 400-yard runway. And then again here, we have player 2 coming in first for 150. Player 3 comes in and adds that 250. Player 1 again contributes nothing because they have that 400 yards already. And then finally, for these ones, player 3 arrives first. So out of the gate, they're paying 400. And then player 1 gets the free ride, player 2 gets the free ride. And then the same thing goes here, 400 out of the gate, 200 contributes 0, and then player 1 contributes 0 as well here. So now we're going to do that same thing here where we break down each of these columns by the sum of each of the values in the column divided by the total number of rows. So for player 1, we're going to have x1 here equal 100 plus 100, or 200, over 6, which if we put this in dollar form, that's just going to be 3333. For player 2, or x2 in our reward vector, we add 50 plus 150 plus 150, or 350 over 6, which is going to be 58 in the third. And then we also have for player 3 here, 250 plus 300 plus 250 plus 250, so 500, 800, 300. Okay, so we've got 1850 over 6 here, and that's going to break down to 308.33. So again, to just kind of conclude, we do have, I'll write it over here on the side, x equals, we've got that 3333 for player 1, 58.33 for player 2, and 308.33 for player 3. This is going to be the Shapley value, or in general, what each of these players should be paying in order to get that full runway paid for so that everyone can use it. And that's going to conclude section 14.7 and chapter 14. Thanks, guys.